Hi everyone. So here's a video with a sort of problem solving example in it that I thought could be useful because we're going to start doing problems of increasing complexity, and this is an example of one of them and an approach you might take in a problem like this. So just to read through the statement of the problem here, it's about an eagle and a bearded dragon. A bearded dragon is a lizard. Um, that's that little lizard right here. This is the bearded dragon right here. And you can see its beard right here, which is a really important feature of this lizard. But the problem goes, an eagle spots a bearded dragon and swoops down near to the ground to catch it. The eagle cruises at a constant velocity of 14 meters per second. When the eagle is 40 meters behind the bearded dragon, the lizard begins to accelerate from rest at 2.4 meters per second away from the eagle. Does the eagle catch the bearded dragon? Okay, so this is interesting because it's a problem that involves two things moving in different ways, and we're interested in if the eagle catches the bearded dragon. So ultimately what we're interested in is there ever a time when the eagle's position is the same as the bearded dragon's position? Which is not necessarily obvious because if you think about what's happening in this problem, it says that the eagle's cruising at 14 meters per second. So let me draw that on here this way. So there's some velocity for this eagle initially. VEI means velocity of the eagle initial, which is 14 meters per second that way. But the initial velocity of the bearded dragon, VBI, is 0, but it has some acceleration. So the acceleration of the bearded dragon is equal to 2.4 meters per second. And also because the eagle is cruising at constant velocity, it has no acceleration. So the acceleration of the eagle is 0. And also the lizard has a head start. So in the picture that's drawn here, the distance between the eagle and the bearded dragon is 40 meters. That distance is 40 meters at the moment when the bearded dragon starts accelerating. So the reason why it's not obvious is because the eagle has some speed at the beginning of this problem and the lizard doesn't. So if the lizard doesn't move, obviously the eagle is going to catch it. But because the bearded dragon starts accelerating, it's possible that it starts moving fast enough, soon enough to get away from the eagle. And that's what we kind of want to figure out. So the basic idea here is that we want to find a time when the position of the eagle is the same as the position of the bearded dragon. If we can find a time when that is true, then we'll know that the eagle caught the bearded dragon. If we cannot find a time when the position of the eagle is equal to the position of the bearded dragon, if there's no time where that works, then we'll know that the bearded dragon has escaped. So the most useful equation for us here will be this equation we derived in class, this one. So the displacement is equal to initial velocity times time plus 1/2 acceleration times time squared. So this says the displacement in a certain time interval, where the time is given by t, is equal to the initial velocity times time plus 1/2 of the acceleration times time squared. That's a result we've derived before, and we can go through that derivation again if you like. It's kind of an abstract equation, but it's really, really useful for us. So we can write down what the displacement of the eagle would be in a certain amount of time, and also what the displacement of the bearded dragon would be in a certain amount of time, because that gets us towards seeing what the positions of the eagle and the bearded dragon are doing over time. So if I write down the displacement of the eagle, that's just, well, the initial velocity is 14 times however much time elapsed, which is arbitrary at this point. So after some amount of time t, the displacement of the eagle will be 14 times t. And also I can write down the displacement for the bearded dragon, which I'll write this way, which is there's no initial velocity for the bearded dragon, but there is some acceleration. So that's 1/2 of the acceleration times time squared. And so the displacement of the bearded dragon is 1.2 times squared, no matter what the time is. As long as it keeps accelerating at that rate, I can describe its displacement this way. But displacement doesn't tell me everything, because the lizard is 40 meters ahead of the eagle when time starts here. So we really want to write displacement another way. If I look at sort of this master equation here, the displacement is really a final position minus an initial position. And so I kind of want to think about what's happening here as I'm trying to figure out when the final positions of these things are the same, if there is a time when they are the same. So I will write that this way. So instead of writing just displacement as 14t, I'm going to say that the 14t is equal to the displacement, which is the final position. I'll call that some variable. So the final position of the eagle, or I guess I'm writing it this way. So the eagle's EF, so eagle final position, minus the eagle's initial position, but let me just call that 0. I can define 0 wherever I want. So let me define the initial position of the eagle to be 0, and I'll write that here. X eagle I equal 0. That's fine. I can do that, which means that the displacement is really just the final position minus the starting position, which is just the final position. On the other side, for the bearded dragon, let me move this equation over a little bit for a little bit more space. Then now I do have an initial position. So the displacement is the final position, which is something after some amount of time, xbf, minus the initial position, which is now 40 in the system that I've chosen, because the bearded dragon starts 40 meters ahead of the eagle, and the eagle starts at 0, so the bearded dragon starts at 40. Okay, so now really what I'm doing is I'm trying to get this final position the same as this final position. If there's a time when those two things can be equal, that means that that's the time when the eagle will have caught the bearded dragon. So let's try to do that. So what I want to do is set those positions equal to each other. So the eagle's final position is 14t, and at the time when the eagle catches the bearded dragon, if there is such a time, I want that to be equal to the final position of the bearded dragon. And if I look at the equation that I have right here, then the final position is just 40 plus the displacement. So that's 40 plus 1.2 t squared. Okay, so now I have an equation that I can try to solve. 14t equals 40 plus 1.2 t squared. This is a quadratic equation. You can plug this into your calculator and you can find solutions for this. There's actually 2 solutions, I think. You can double check me on that. I get that time is equal to 5 seconds or 6 2/3 seconds. So 2 answers, which is kind of interesting. And we should talk about what that means. But basically there is a time, at least one time, where the positions, the final positions of the eagle and bearded dragon are the same. So yes, the eagle does catch the bearded dragon and probably eats the bearded dragon for dinner, which is sad for the bearded dragon, but happy for the eagle. So to interpret these 2 routes and to sort of approach the problem from a different perspective, I want to show you something in Desmos. So give me 1 sec to pull that up. Okay, so this is a Desmos plot of the final position of the eagle, which is the red line, and the final position of the bearded dragon, which is the blue line. And you can kind of see what happens here. So the eagle's moving at constant velocity. So the eagle's position just increases linearly in a straight line. That's pretty cool. And the bearded dragon's position increases quadratically. And you can see that there is an intersection point right here at 5. So actually, this tells us both that the eagle catches up to the bearded dragon at 5 seconds, and also that happens 70 meters from the initial position of the eagle. or 30 meters from the initial position of the bearded dragon. So that's kind of cool. And this gives actually a little bit of intuition about what that second time is. So if you look at the other intersection point of this curve, where the two positions are equal at 6 2/3, you can, so what that means is if the eagle just flew past the bearded dragon without catching it, let's say, and they both continued their motion. So the bearded dragon continued to accelerate at the same rate, and the eagle just continued to fly at 14 meters per second. Then the eagle would fly past the bearded dragon, but then at 6 2/3 seconds, then the bearded dragon would now catch up to the eagle and then run past it. So at the first point when the eagle catches the bearded dragon, that's probably where it's gonna like sink its talons into the bearded dragon and eat it. But if it didn't, if it just flew past and everything continued the same, then the bearded dragon would then surpass the eagle at this point, at this second route. So that's kind of the meaning of the two routes. And for our problem, really, just because of the statement of the problem and the meaning of what's happening, we really only care about this first route. That's when the eagle catches the dragon for our purposes. So I hope that helps think about this kind of problem and a way to approach it, and how you can use that kind of abstract equation, displacement equation, VIT plus 1/2 AT squared, in sort of a complicated problem solving situation. So yeah, I hope it was helpful, and I will see you guys soon. Bye.